The super lathe is the most productive and dependable roll lathe built. Designed and built specifically for steel mill duty, it holds the record for minimum downtime over a 20-year period. The super lathe concept is based on three fundamental parameters: rigidity, backlash, and hysteresis. The goal is to maintain extreme rigidity, zero backlash, and zero hysteresis. No item in design or manufacturing is too small or insignificant to be considered. Each improvement contributes to a substantial improvement in the lathe. No compromise is made in design. All parts must be manufactured, fit, and assembled to match the required design. To make the system complete, the tooling is designed using the same principles. A chain is only as strong as its weakest link. The tooling is just as critical to the success of the cut as any other part of the machine. When this method of designing and manufacturing is followed, amazing results are obtained. Capabilities assumed to be impossible become practical and beneficial. Now torsional rigidity, backlash, and hysteresis in the gear train are tremendously improved by running the gear teeth with true zero backlash instead of the AGMA class of zero backlash. The gear teeth can even be run with preloaded interference fits with no detrimental effects. The design of the lube and cooling system is engineered to suit that particular gear train as a whole and provide temperature compensation to automatically maintain the interference fit and bearing loads within acceptable limits. Super lathes with preloaded gears which have been running for over 20 years still show the original grind finish on the flank of the teeth. The results from using these techniques of design and manufacturing. This chip, cut from forged mild steel bar, shows what a super lathe can do with conventional material. Our goal, however, is to machine the unmachinable material, which is made up of high percentages of cementite and alloy carbides, martensite, and bainite. You'll soon see the super lathe machining the unmachinables. This spindle assembly is being inserted into the headstock housing by threading it through the bore. Then the main bearing at the bottom of this picture is set up and preloaded to allow the spindle to rotate on the axis of the front bearing. Then the rear plate, not shown, which will retain the rear bearing, is placed over the assembly to close the gearbox. The bore for the bearing in the rear plate can then be trammed from the spindle assembly to position the rear plate directly in line with the axis of the front bearing. This technique ensures that all 4 rows of bearings on the same shaft are in alignment and will produce a true running spindle. Runout errors of 1 to 2 ten-thousandths of an inch total indicator readings are obtainable even on very large bearings with bore diameters of 20 to 40 inches. This is a 400 horsepower 2-speed headstock on a 40-inch super lathe with a 2-jaw floating chuck. This work driver will provide full torque transmission to the roll with greater rigidity than a 4-jaw chuck. It will not push the roll off-center since all radial forces are balanced. The motor and gearbox cover have been removed to show the details of the lubrication and cooling systems. Twin motors on the rear of the headstock each drive a separate pinion on the bull gear. The 2 pinions provide more torque and power in the same size headstock and also increase the torsional rigidity and electrical response of the drive. The tailstock of a 60-inch super lathe shows all the ergonomically located controls when viewed from the loading position. The hydraulic power and lubrication system of a tailstock are seen when the cover is removed. The rectangular quill at the top right of the tailstock is 2 1/2 times as rigid as a round quill in the same space. This unique design eliminates the need for clearance found in a conventional round tailstock barrel, allowing instead for an interference fit. This type of fit then makes the quill clamping automatic while still allowing for thermal expansion of the roll. The saddle of a 40-inch super lathe is turned upside down to show the anti-friction way construction with the fully hardened bedway bar in place. One of the most important mechanisms for reducing hysteresis is the anti-friction way system on which moving members must travel. These linear ball and roller bearing ways are superior because they can be preloaded and their static and dynamic coefficient of friction are very low. This weigh bar has 20,000 pounds of preload, yet it can be easily moved with one finger. In addition, friction coefficients can be regulated to produce the most desirable characteristics. The best performance for high precision work can be obtained if the friction remains constant at a very low level, regardless of the size of the applied load. This moving carriage has a dead weight of 40,000 pounds on the ways and an additional load capacity of 60,000 pounds. The force required to move it along the ways with dead weight is only 150 pounds. As the active load increases up to about 10,000 pounds, the 150 pounds of friction force remains about the same. Then from 10,000 pounds to about 20,000 pounds, the friction force drops slightly. As the load is increased from 20,000 pounds to the active limit of 60,000 pounds in the rough cutting range, the frictional force increases at about the same rate. When the load is decreased, the original precision characteristics return to their original state without any long-range loss of performance. Thus, the machine is fully capable of both roughing and finishing. This weigh bar is the primary guide way for alignment of the carriage motion and will take forces in any radial direction about the axis of the bar. The overturning moments are taken by a second weigh bar at the opposite edge but not shown. The ball nut and zero backlash gearbox are mounted on the surface between the two weigh bars, which will be mounted on the bed lengthwise. These ball weighs are linear ball bearings with recirculating balls and are one of our earlier patents, dating back to 1956. These weighs are extremely sensitive to high-gain servo control without sacrificing capacity or accuracy. They are shown here with the covers and seals removed. Since dirt and contamination do not cause the problems found with sliding weighs, these weighs do not need elaborate covering systems, which have proven to be unreliable on other machines. The weighs have long life without adjustment. Some machines have been in steel mill service for 20 to 30 years, running 24 hours a day, and have never been adjusted. The cross-slide weigh cartridges that are mounted on top of the saddle are shown here at the bottom of the picture because the saddle is upside down. These weighs carry the tool post, which ties the two cartridges together, and are identical to the saddle ball weighs, but preloaded to 10,000 pounds each. The tool post of a super lathe has one tool in cutting position and four more in the tool changer to the right. These tools embody all the criteria for rigidity and are 5 inches square, weighing about 150 pounds. All tools are qualified for X and Z gauge length to within 1/1000th of an inch and take about 90 seconds to change. The support snout that extends all the way out under the cutting edge transfers the cut force on the tool directly into the main structural members with virtually no bending stress in the tool shank. The tool shown can remove material at a rate of 20,000 pounds per hour from heat-treated alloy steel of 30 Rockwell C hardness in a cut which is 6 inches off the diameter. The resultant chips are heavy enough to be charged directly into the electric furnace for remelting. After the bulk of the material has been removed with the tool types just shown, this quick-change cartridge tool can be used to finish complex shapes and contours. It can be changed in 30 seconds and is capable of taking feed forces up to 10,000 pounds on the Z-axis and 20,000 pounds on the X-axis. All of the cartridges are qualified to 3/10,000ths of an inch on the gauge lengths for both axes, and with a little experience, an operator can match up blending contours to 1/10,000th of an inch, even though the machine may be using more than one tool shape to finish different portions of the same contour. The tool shown here is a 1 1/4 inch diameter button. Now, the button cartridge is being changed to a different shape. The clamping geometry is unique. It is designed to have all clamping forces remain in compression under all cutting conditions. This is the cut of which we are most proud. It is the first high-powered hogging cut ever made using a ceramic cutter. It was made at the time when many in the metal cutting industry believed ceramic cutters could only be used at very high speeds on very light cuts. However, our detailed analysis indicated that it would do very well. So, despite the expert's opinion, It was successfully used anyway for roughing. This is the type of cutting the super lathe was specifically designed to do. Each of the cuts you are about to see have been selected to illustrate performance which is not attainable on conventional machine tools, but is routine on the super lathe. Almost all chips produced are type 2 or 3 segmentations. Even chips from a 200 horsepower finishing cut producing a 20 to 30 micro-inch finish are segmented to a large degree. This segmentation did not disturb the finish. On conventional machine tools, the induced vibration of such segmentation would preclude any possibility of high finishes. This material was cut at 300 feet per minute with a 45 thousandths of an inch per revolution feed using a ceramic insert set at a 45-degree lead angle and 5-degree negative rake with a 3/1000 of an inch wide K-land at 30 degrees to the top. The cut was 2 3/4 inch diameter reduction, which made the chip 2 inches wide. Note the texture of the chip. It is a continuous ribbon, but is virtually a Class 3 chip, completely segmented except for an occasional spot holding the segments together. When held up to the light, it looks like a piece of fine lace. Now, we will show the actual cut in progress with the same insert and chips just seen. The material is chilled alloy iron with 15% cementite in a perlite matrix. The Brinell hardness number is 430. The chips come off in a smooth, continuous ribbon, indicating high rigidity instead of flying off like metallic chaff. The undulating contour of the roll combined with rust, mill scale, and deep fire cracks make it very difficult to cut. Despite this, the camera resting on the tailstock shows no vibration in the machine while a smooth cut is being made. The cutter is almost pure aluminum oxide made by Stupalox Company in 1958. It was a very hard but brittle material and performed extremely well on the super lathe. It was a total failure on conventional machine tools due to inadequate rigidity in the machines and tooling. This example is a 52-100 forged steel roll at 195 Brinell hardness number with a large overlay and crack at the end, running 1.5 inches deep by 11 inches long. It is a disastrous situation for conventional machine tools, but is gobbled up on the super lathe. The forging scale on the surface and in the overlay adds greatly to the difficulty, but a reduction of about 20% in cut speed to 250 feet per minute is all that is needed to compensate for it. As the crack passes over the cutter each revolution, you will notice a puff of dust, which is the result of the scale within the crack being suddenly pulverized by the cut force and chip formation. The carbide cutter is a newcomer graded 3268 set at 5 degrees negative with 45-degree lead angle. The feed is 60 thousandths of an inch per revolution. Cutter life under these conditions is 30 to 40 minutes. Starting a new cut on the adjacent shoulder in sound metal, the cut speed will be increased to 325 feet per minute and the feed to 70 thousandths of an inch per revolution. Now it is shown in slow motion to illustrate the chip formation. Notice that as the eccentric forging uncovers the tool interface, the surface temperature is about 1400 degrees Fahrenheit and still cutting. After the scale has been removed, subsequent cuts can be made using more than 350 feet per minute with 80 thousandths of an inch per revolution at depths of cut up to 3 inches, requiring 500 horsepower and producing 17,000 pounds of chips per hour. This is an energy rate of metal removal in steel of 2 cubic inches per minute per horsepower. This is a full-powered cut in similar material. Notice the rate of accumulation of chips. Without automatic chip disposal, they can be overwhelming. Each chip is 5/8 of an inch wide and represents 100 horsepower. These are the inserts and the respective chips, 5/8 of an inch square by 3/8 of an inch thick. A similar cut is shown in high tensile cast steel with 22% cementite in a bainite matrix, which must be cut at relatively low speed. This cut is taking high torque of about 55,000 pound-feet, but not full horsepower. The pencil is standing on the cutter shank without a quiver. The material is adamite, with a tensile strength of 100,000 pounds per square inch and 55 shore hardness. It is cut at 140 feet per minute and 50 thousandths of an inch per revolution feed rate. This is an induction-hardened forged steel roll. It is quenched and tempered martensite at Rockwell C61, about 7/16 of an inch deep. Below that is a transitional layer 3/16 of an inch thick at Rockwell C58 down to the core at Rockwell C28. The 5/8 inch deep cut removes both the hard case and the transitional layer at the same time at 300 feet per minute at 18 thousandths of an inch per revolution using cubic boron nitride cutters. 2 inserts are cutting, making 2 separate chips. The chip from the hard case is coming off to the left and breaking into short pieces. The chip from the softer part is coming off to the right in longer ribbons. The cutter life is 28 minutes per edge. The difficulty in this kind of a cut is to get satisfactory performance on 2 radically different materials at the same time with the same cutting edge. This is a plunge cutter with a 5-inch wide cutting edge. It is made of multiple inserts laid end to end to make a long edge. This is used to cut very hard chilled alloy iron, such as this 45% cementite and 65% bainite and martensite, with an average hardness of Rockwell C61. In the cast skin, the cut speed is 60 feet per minute with 10 thousandths of an inch per revolution feed. Below the skin, the speed is 90 feet per minute with 13 thousandths of an inch per revolution feed. Even though this is a very brittle material, the chip still comes off in a continuous ribbon. The carbide cutters are carbaloy grade 895 in the skin and grade 999 below the skin. These are typical chips rolled up like toilet paper. This is a lap cutter for high-powered, fast finishing of shallow cuts. 1/16 of an inch is removed from the diameter to produce a 20 to 30 micro-inch finish using 200 horsepower on a high-tensile cast alloy steel roll with 18% cementite and the balance of bainite. This roll is 27 inches in diameter. The linear feed rate is 19 inches per minute. Hardness is 55 shore. Again, a plunge cut in similar material removes the 16-inch fillet radius in the transition from the large diameter body to the much smaller neck, which was required by casting procedures. The eccentric runout of the casting is a few inches, which has no impact on cutting action. In 3 plunge cuts, the entire 16-inch radius is roughed out and ready for a single contouring finish cut. The cut is made with carbaloy grade 350 at 250 feet per minute and 40 thousandths of an inch per revolution feed, giving a cutter life of 45 minutes per edge. The cutter shank is 5 inches square, which can be used to scale the relative sizes of the rest of the parts. This material is adamite, which is 80,000 psi tensile and 45 shore with 15% carbides and 85% bainite and some pearlite. This is a parting cut on a 31-inch diameter roll of similar material. It has a Brilno hardness number of 450, but is very tough, strong, and abrasive. The parting tool is a 1-inch square carbide insert set at 45 degrees, which makes the groove 1 5/16 inches wide. The chip is splitting right down the apex of the angle, making the halves considerably narrower than the slot. The cut speed is 120 feet per minute with 40 thousandths of an inch per revolution feed. After only 3 minutes of cutting, the cut is 3 inches deep. With constant cut speed, as the cut diameter decreases, the linear feed rate increases. This is a cut with a 1 1/4 inch diameter button. A series of adjacent plunges are being made to rough out a toroidal groove of 7 1/2 inches in diameter and 180 degree of arc in a mild steel-forged bar 27 inches in diameter. Each successive groove gets deeper toward the center of the torus, then shallower beyond the center, stopping just short of the finished size. The scallops are then removed with the same cutter insert using a single circular contouring cut. For final finishing, the insert is changed to ceramic, which removes the last 1/32 inch of material. The entire operation requires only 7 1/2 minutes. This is a skip turning tool shown in slow motion. It is used to turn a portion of a diameter that has protuberances extending up from that diameter, such as lateral ribs. This particular tool will skip 1 1/4 inch high rib with a retraction time of 6 milliseconds and a re-entry time of 7 milliseconds. To demonstrate the stability of the super lathe, a nickel was placed on edge close to the cut at the end of the tailstock quill. Even though the cut is interrupted and the tool is jerked in and out twice each revolution, the nickel continues to stand. This sequence is run at standard speed to give a true picture of the operation. The workpiece is a conical 410 stainless steel tube, which after turning has a wall thickness of 3/16 of an inch, with a series of annular and lateral ribs that stand 1 inch above it. To skip turn the part, narrow pockets are first machined alongside the lateral ribs to allow space for the skip tool to enter and exit the cut on either side of the rib. Then it is placed on an expanding mandrel to support the thin-walled section against the heavy interrupted cuts. By machining it this way, the savings is about 10 to 1 over the previous method of milling the part completely. The skip tool superimposes a fixed retraction onto the normal movement of the saddle and cross slide, and can be timed to skip multiple ribs anywhere around the workpiece. As you can see, after many skips, the nickel is still standing exactly where we placed it. This is another example of a difficult and unusual job. It is a conical thread 16 inches in diameter at the large end and 10 inches at the small end. It is 21 inches long with a 1-inch pitch. This forging is made of high alloy medium carbon high tensile steel. It is 33 feet long and must be cut to very close tolerances. The threads are chased out of solid at 100 revolutions per minute. This is the top and middle roll from a 3-high rail mill stand. The top roll is 39 inches in diameter with a body 66 inches long. The material is perlitic nodular iron with a hardness of 57 Shore. It contains 25% cementite with alloy carbides. The recutting of this roll, having been worn out of tolerance from rolling, took only 239 minutes. The refinished accuracy was 5/10,000ths of an inch from true shape. The deepest groove is 9 inches in pass number 2 and is 1/2 inch wide at the bottom with 1/16 inch fillets in the corners. The investment in the super lathe is well worth the time and effort. If there is enough work to keep the machine busy around the clock, the return on investment can be immense. The average payback experience so far is $3,000 per day and has ranged as high as $10,000 per day. The question is, can I afford to buy a super lathe? If I have sufficient work, the real question is, can I afford not to buy it? Super lathe is the registered trademark of Binns Machinery Products, Cincinnati, Ohio, USA.